Today we will be presenting a case study on the laboratory explosion involving the synthesis of trimethylsilicazide or TMSazide that occurred at the University of Minnesota on 17 June 2014. Laboratory accidents involving hazardous chemicals continue to be a major concern because they can result in serious injuries, property damage, and environmental pollution. Azide compounds are widely used in chemical synthesis due to their versatility, but they are also highly toxic, unstable, and potentially explosive if not handled properly. Although this accident occurred in the United States, the lessons learned are highly relevant to laboratories in Malaysia. Throughout this presentation, we will relate the incident to Malaysian regulation, including the Occupational Safety and Health Act 1994, OSHA 1994, the Occupational Safety and Health Use and Standards of Operation of Chemicals Hazardous to Health, Regulation 2000, the Class Regulation 2013, and the Industry Code of Practice on Chemical Classification and Hazard Communication. This regulation emphasizes chemical risk assessment, safety data sheets, hazard communication, and safe laboratory practice. Incident occurred on 17 June 2014 in a chemistry research laboratory at the University of Minnesota during the synthesis of trimethylsilicazide, also known as TMSazide. During the experiment, a graduate student attempted to scale up the reaction from a small laboratory scale to a larger quantity. At the same time, several reaction conditions had been modified from the original procedure without a comprehensive hazard evaluation. As the reaction progressed, an unexpected detonation occurred, causing a powerful explosion that severely damaged laboratory equipment and facilities. Fortunately, no fatalities occurred, but the incident highlighted the danger of handling energetic chemicals without adequate risk assessment. This accident serves as an important reminder that even experienced researchers must carefully evaluate every procedural change before carrying out laboratory work.
Then we have the primary reactants and their inherent hazard profiles. First up, we have sodium azide with a chemical formula of NaN3, and its general name is sodium azide. The trade name or brand name is hydroxide acid sodium salt, or azide or smite, often distributed as an industrial or laboratory reagent by brands like Sigma Aldrich, Thermo Fisher Scientific, or Merck. The CAS number is 26628-22-8. And finally, the molecular weight is 65.01 grams per mole. Then we have trimethylsilyl chloride with a chemical formula of CH3,3SiCl. The general name is trimethylsilyl chloride or chlorotrimethylsilane. The trade name or brand name TMSCI or TMS chloride or Centrosil, which is often distributed as a synthetic or silylating reagent by brands like Sigma Aldrich, Across Organics, or Alpha Acer. The CAS number is 75-77-4. And finally, the molecular weight is 108.64 grams per mole.
The goal of the experiment was a standard nucleophilic substitution reaction. The two starting materials were supposed to react to form our target liquid, trimethylsilicazide, TMNNS3, plus a salt byproduct. In chemistry textbooks, TMNNS3 is famous for being a safer alternative to pure dangerous explosive acids. Because it was considered safer, the lab crew became comfortable. The student had successfully run this exact experiment over 10 times on a small 100-gram scale. Assuming everything would be fine, the student decided to double the size of the batch to 200 grams. But in lab safety, doubling the scale does not just double the risk, it multiplies it. When you increase the amount of the mass, the reaction creates much more heat, making it incredibly difficult to cool down safely. This slide explains the exact change that caused the disaster. The standard proven procedure explicitly requires a solvent called diglime. Diglime is light, thin, and completely dry. It allows a magnetic stirrer to spin easily, which distributes heat evenly so the flask doesn't overheat. However, for this specific run, the students swap out diglime for polyethylene glycol 300 known as PEG 300. The solvent swap introduced two fatal flaws. First, PEG 300 is incredibly thick and viscous. Because the student did not use a heavy-duty mechanical stirrer, the mixture clumped, making uniform stirring impossible. Second, PAG300 acts like a chemical sponge. It naturally absorbs trace moisture from the air. This unknowingly traps water inside a moisture-sensitive environment. Now, let's trace the exact chemical path to the explosion. The trace water trapped inside the thick PAG300 solvent caused an unintended side reaction. It reacted with the sodium azide and generated a highly dangerous compound called hydroxide acid. Hydroxide acid is a nightmare for lab safety. It has a boiling point of just 37 degrees Celsius, meaning it turns into vapor very easily. It is also brutally shock sensitive. When the student heated the system to purify the liquid, the hydroxide acid vaporized, traveled up the glassware, and condensed back into a pure explosive pool at the top joints. Because the thick solvent wasn't stirring properly, hot spots formed at the bottom of the flask. This heat triggered the ultra-sensitive hydroxide acid pool. It is instantly detonated, shattering the glassware and completely destroying the fume hood. This proves that changing even a single variable like a solvent can cause catastrophic chemical reaction.
Moving on to our next section, let's look at the chemical profile and toxicity analysis. On this slide, we are comparing two specific substances, trimethyl silyl azide and sodium azide. Understanding their physical properties and hazard rating is important for our safety and handling protocols. Let's break down one by one. First, let's look at trimethyl silyl azide, as known as azidotrimethyl silate, with the chemical formula of TMS and 3. Physically, this is a clear, colorless to straw colored liquid. It has a boiling point of 95 to 96 degrees Celsius and highly volatile. It is a very low flash point of just 6 degrees Celsius, meaning it catches fire easily at room temperature. If we look at its NFPA 704 diamond rating, it scores a 3 for health and a 3 for flammability, making it a high-risk substance for both exposure and fire. Its instability is rated at 0. Under Globally Harmonized System, or GHS, is formally classified as Category 2 flammable liquid, alongside a Category 3 acute toxicity rating across all primary exposure routes, oral, dermal, and inhalation. Now let's look at the second chemical. Sodium azide is a white crystalline odorless solid. It has a high melting point of approximately 275 degrees Celsius and has no flash point, meaning it does not present the same immediate liquid flammability risk. However, its hazard profile shifts in other areas. Its NFPA rating shows a 4 for health, which is a highest level of toxicity hazard. It has a flammability rating of 1, but its instability jumps to 2, indicating a violent chemical changes or reactivity. This extreme toxicity is reflected in its GHS classification. It is a Category 2 for acute, oral, and inhalation toxicity, even more severe Category 1 for dermal exposure, and it also carries a Category 1 classification for aquatic chronic toxicity, meaning it poses a severe long-term threat to the environment. Next, let's take a look at our third compound in this toxicity analysis, hydroxide acid, also known as hydrogen azide. Physically, it's a colorless, highly volatile liquid. What makes it particularly hazardous? Its low boiling point of just 37 degrees Celsius, which is a human body temperature. Its flash point is extremely low and highly explosive, meaning it can easily vaporize and ignite or detonates under laboratory condition. Looking at its NFPA 704 rating on this slide, it is a 3 for health, indicating severe and deadly exposure hazard, and a 3 for flammability, reflecting its high risk of ignition. Its GHS classification show how important the handling protocols are. It is classified as Category 1 flammable liquid, the highest risk level for flammability, and Category 1 for acute toxicity across all 3 routes. This means even minimal exposure or small spill can be fatal. To help contextualize this number, the right side of our slide features the standard NFPA 704 diamond. Starting with the regulatory framework governing this case, we look at OSHA 29 CFR 1910-1450, commonly known as the laboratory standard. This standard legally mandates that the research institution establish and strictly enforce a written chemical hygiene plan to ensure worker safety. A core requirement here is to exposure protection, meaning the lab must use proper containment to keep toxic vapor well below established permissible exposure limit. In this specific incident, the generation of highly toxic hydroxide acid gas directly violated this threshold. Regulations state that strict limit for this gas is 0.1 ppm, aligned to prevent acute poisoning and severe vasodilation in lab personnel. Next, in risk assessment and standard operating procedure, regulation clearly dictates that high hazard, shock-sensitive chemical reaction must follow a peer-reviewed SOP. The researcher in this incident breached these safety mandates by taking a massive shortcut, executing a dangerous tenfold scale up and a complete solvent substitution without any formal risk authorization. Furthermore, proper pre-screening protocols were entirely ignored. The lab failed to utilize standard predictive software or hazard database tools such as chemical reactivity worksheet or chemicals. Finally, let's look at the failure of physical and administrative containment control. Because azide compounds are inherently volatile and shock sensitive, regulatory guidelines demands heavy engineering barriers. Any unpredictable distillation must be performed strictly behind a physical, heavy-duty blast shield inside a certified fume hood with a protective sash pulled fully down. This basic protection was entirely missing. On top of that, there was a total failure in administrative oversight. Because this highly hazardous reaction was left running unattended overnight, explicit unintended experiment signage was legally required on the hood facade. This important warning sign must display the hazard type and emergency contact info to protect the emergency responder.
Then we have the possible failures in safety and health management which led to the incident happening. First reason is the flawed hazard assessment and lack of documentation, and under that is the inadequate experiment planning, which the students failed to prepare or identify the hazards of the solvents that they changed or the scale up that they did for the experiment. Secondly, they didn't have a standard operating procedure SOP for the scale up procedure when they increased the mass of the original starting material from 100 grams to 200 grams. This could lead to unaccountable or unpredictable circumstances. Moving on to the operational and process failures. The first one under operational and process failures is the excessive scaling without approval. This is met by the students not seeking approval before scaling their starting material from 100 grams to 200 grams. Then the unapproved procedure changes means that the students didn't also seek approval for their procedural changes in which they changed the original solvent into a PEG 300 solvent, which is a very highly hygroscopic substance. This allowed for the reaction to this solvent to absorb moisture and introduce moisture into the reaction. Moving on to the lack of controls and physical safeguards, and the first one under this category is the missing engineering controls. What is meant by missing engineering controls is that despite the students knowing they are experimenting with a larger mass or larger amount of starting material which is highly reactive, they should have prepared a blast protection or a blast shield under the fume hood to protect themselves from any possible explosions. Secondly, the improper apparatus setup. In the experiment, the students didn't use a mechanical stirrer which should have been present, and this could have caused an overheating in the reaction during the stirring. Thirdly, absence of personal protective equipment, PPE, and awareness. The students in the experiment failed to wear their proper protective equipment that would have protected themselves from the extremely hazardous experimental setup. Finally, systemic safety management failures, and the first one under this category states that the deficiencies in chemical hygiene plant CHP boundaries. And in the report, it states that the CHP boundary was not clearly defined before the incident, highlighting a gap in institutional oversight. Secondly, gaps in lab safety culture and communication. Despite the students having prior experience to similar experiments before, there was a failure in day-to-day hazard communication and peer review within the research group itself, which led to disregarding the risks and this specific high-stakes experiment.
Moving into the specific consequences of this incident, we must first address the severe human toll. A fifth-year chemistry graduate student was operating the controls when the detonation occurred. Because the fume hood sash was open and proper personal protective equipment was not utilized, the student absorbed the direct impact of the blast wave. The physical injuries were extensive. The student sustained painful second-degree burns across his body. Flying glass debris from the reaction flask acted as shrapnel, causing deep laceration to his arm and his side. Additionally, the sheer acoustic pressure of the explosion ruptured the student's eardrum, resulting in immediate temporary hearing loss. Beyond the immediate victim, the blast endangered everyone in the vicinity. Over 50 personnel working inside Smith Hall experienced the trauma of an active emergency. They were forced into an immediate building-wide evacuation as the emergency responded rushed to stabilize the facility. Next, let us look at the physical destruction within the laboratory infrastructure. The force of the 200-gram scale-up synthesis was completely devastating to the physical room. The primary fume hood, where the reaction took place, was entirely demolished internally. The structural integrity of the unit was compromised so badly that it had to be permanently decommissioned. The destruction was not isolated to a single bench. The shockwaves traveled laterally across the room, causing significant collateral damage to a neighboring hood. It also blew outward, shattering a large exterior window of Smith Hall and showering glass onto the surrounding campus area. From an environmental standpoint, we escaped a worst-case scenario. The investigation confirmed that there were no secondary toxic chemical spill outside of the immediate laboratory boundary. Furthermore, the blast did not ignite any second fires. However, the local lab environment was left entirely unusable, heavily disrupting months of academic research. Next slide, which details the immediate technical and engineering overhauls resulting from the UMN investigation. The first and most critical lesson was that researchers cannot scale up hazardous reaction without rigid, predefined boundaries. To fix this, the university updated its chemical hygiene plan to enforce strict chemical scale boundaries. Specifically, they instituted a mandatory 5-gram threshold for all high-risk azide reaction. If a researcher wants to exceed 5 grams, they can no longer just do it on their own. They must clear a rigorous formal safety review board first. The second lesson, the historical literature for TMS azide explicitly stated that the reaction must be shielded. Moving forward, the department mandated that all potential volatile reaction must be conducted strictly behind heavy physical blast shield or safety screens. Additionally, this incident highlighted the hidden dangers of making minor process modification, like changing solvent without a formal technical review. The student had swapped diglum for PEG 300, which trapped moisture and created explosive hydrozoic acid. Because of this, the university made it compulsory to use explosion-proof laboratory equipment and mechanical stirrers to prevent localized overheating. Most importantly, any changes to a reaction, solvent or protocol now strictly requires a brand new peer-reviewed standard operating procedure before any chemical are mixed. Lastly, the university recognized that technical fixes are useless without a complete change of human communication and safety culture. The investigation revealed that hazard communication at the bench level had broken down. To solve this, the department introduced physical safe operation cards. These are highly visible standardized forms that must be filled out and clipped directly to the front of fume hood while an experiment is active. This card explicitly displays the running temperatures, pressure and chemical hazards and emergency contact info, so anyone walking by instantly knows the status of the hood. Furthermore, the department realized that safety dialogue must be continuous habit, not a reactive afterthought.
They mandated that every single research group meeting must now begin with a dedicated short safety moment. This forces researchers to openly discuss upcoming protocol changes, analyze worst case scenarios, and share safety warning before stepping up to the bench. Finally, they shifted the entire department towards bottom-up accountability by empowering the student that join safety team to conduct peer lab audits. These structural changes targets the ultimate root cause of the incident, complacency. We must actively eliminate the false sense of security that develops when small-scale runs go smoothly, because scale-up procedures introduce unpredictable catastrophic risks. Thank you.
Although the laboratory explosion occurred at the University of Minnesota in the United States, a similar accident could also happen in Malaysia if hazardous chemicals are not handled properly. Fortunately, Malaysia has several regulations designed to prevent incidents like this. First is the Occupational Safety and Health Act 1994 or OSHA 1994. These acts require employers and educational institutions to provide a safe working environment, identify workplace hazards, and implement appropriate safety measures to protect students, researchers, and laboratory personnel. Secondly is the USEC HS Regulations 2000, which focus on the safe use of chemicals that are hazardous to health. This regulation require proper risk assessment, safe handling procedure, exposure control, employee training, and the use of appropriate PPE equipment. Third is the class regulation of 2013. These regulations ensure that hazardous chemicals are correctly classified, labeled, and accompanied by safety data sheets. This allows laboratory users to understand the hazards of chemicals such as trimethylsilyl before conducting any experiment. In the University of Minnesota accident, better hazard identification and risk assessment could have reduced the likelihood of the explosion. Similarly, strict compliance with this Malaysian regulation can help prevent laboratory accidents by ensuring that hazardous experiments are properly planned, assessed, and carried out under safe conditions. In conclusion, the lab explosion in University of Minnesota in 2014 highlights the severe risks involving the handling of hazardous chemical without proper hazard assessment. The accident were identified as a result to inadequate assessment of hazard and risk and unawareness of chemical explosive properties. This incident served as a reminder to implement effective chemical health and safety management to ensure the safety of personnel and the work environment.